A warm welcome to the second session of Biopolymer and Molding, the International Congress on the Future of the Plastics Industry. I hope you have enjoyed lunch and feel replenished for the second session of our Congress. The second session will focus on processing biodegradable plastics. During the lecture, you will again have the opportunity to ask your questions, so please feel free to join in the chat using chat function. You place your questions there, which will then be happy to forward to the speakers. I'm now very pleased to welcome my colleague, co-organizer and fellow POLYKUM member, Dr. Patrick Hirsch. He has been researching the microstructure of materials for some time in order to apply this knowledge and produce virtual mixtures as needed. At DigiLab, he has developed a method for finding optimal formulations and suitable process parameters for processing plastics. This effectively saves costs, personnel expenditure, and time-consuming test series. Peter, DigiLab has entered into cooperation with POLYKUM. What motivated you and POLYKUM to participate in this project?
Yes, at first, when Patrick proposed it, I was skeptical. Then just curious and wondering what will happen. In fact, I didn't understand what those computer nerds are talking about, and I'm sure this was vice versa. But when I saw the first results, not only the database, but also the proposal for new compounds, the prognosis, and the virtual part, it was amazing. It has loads of potential. We will show it on the KAI Fair in Düsseldorf this year live. It is absolutely astonishing when you set up your VR Google and enter the room with properties and colors. It is an attraction also for young people. In fact, with our topics biopolymers and digitalization, we don't have any problems to interest young folks, and we have really no hiring problem.
That's very promising. Welcome, Dr. Patrick Hirsch from the Fraunhofer Institute for Microstructure of Materials and Systems, IMVS, with the presentation on virtual material development for thermoplastic biopolymer compounds. Here is the film.
Hello, my name is Patrick Hirsch. I'm a co-worker of the Fraunhofer Institute for Microstructure of Materials and Systems. And today I would like to show you our latest work on the virtual material development for thermoplastic biopolymer compounds and our DigiLab platform we have developed for this. If you look to this picture, you see our former Chancellor, Ms. Merkel, and what she is doing. This is what we are doing. We are looking into the microstructure of materials. We try to understand how materials are built up at the nanoscopic and microscopic level, and then try to use this knowledge to customize the macroscopic properties of these materials. And you can see that we work with different kinds of materials in our business units. And the business unit I'm working in is the business unit of plastics. And in here, biopolymers or sustainable materials play a major role since many years. And we help our customers and the local industry to develop new materials and parts with these products. So what is the actual situation? On the left side, you can see the plastics production over the last years. And here you can see the trend which was ongoing since many decades. So plastics production had a strong increase since many, many years and went up to a maximum of 368 million tons in the year 2019. In the last year, due to the pandemic situation, however, we had a small decrease, but the increase will go on. The world population is still growing, and therefore the production and the use of plastics will further increase. What are the main market segments for plastics production? You can see that by far the biggest market segment is packaging. And in here, mainly polyethylene and polypropylene are used as materials. And those materials we want to replace by sustainable materials like biopolymers. Here you can see the general properties of polyethylene and polypropylene. In general, those materials are well suitable for packaging, so they have good strength and good stiffness, also good strain and break and impact strength. And since a few years already, also bio-based polyethylene and bio-based polypropylene are available. One major backdraw anyway is that they are not biodegradable. And this means that if those products end up in the nature, they will not decompose and will stay in the nature and will at the end come to our food chain as microplastics. And this is a big problem. We want to contribute by the development of new biopolymers. And you can see one of those biopolymers is PLA, polylactic acid. This is a thermoplastic biopolymer, which is also available in the market since many years. And you can see that this material has good stiffness and strength, but is quite brittle. So the strain and break and the impact strength are very low. But as mentioned, it is bio-based and it's biodegradable. So the sustainability in comparison to polyethylene and polypropylene is improved. However, there are other biopolymers entering the market right now, and one of the most interesting of those is PBS, polybutylene succinate. And here you can see that this material has very good ductility, so high strain and break, high impact strength, and is also bio-based and biodegradable. And especially in combination with PLA, there are many options to design and to compound polymers and mixtures which can easily compete with polyethylene and polypropylene. Here are recent market data for those bio-based and biodegradable polymers. And you can see that especially for PLA and PBS, the shares are increasing, and PLA actually has a share of 18.9% of the global biopolymer market within the range of the biodegradable materials. PBS just has 3.5%, but this share in the future will strongly increase. And as mentioned, those two materials are very interesting for replacing of polyethylene and polypropylene. So what are the tasks if you want to design or develop new polymers, new compounds? At the beginning, you always have a requirement profile of your material where the needed mechanical properties, processing properties, and so on are listed. And this gives the start for the optimization cycle you will enter. So first step is compounding, real mixing of new materials. The second step is production of test specimen, in most cases by injection molding. And later on, you will do the testing, for example, tensile testing, and those tests are then analyzed. And if the requirements are met with the test results, you are done and you can leave this optimization cycle. If not, then you have to repeat the cycle so often that you have your requirement or required properties. And in real, this can end up in many, many experimental trials, and this is very cost and time consuming. However, at the end, you have your compound and you can produce your part. And if something changes with the part or with the requirement profile, you have to start the optimization cycle again. We want to improve this by usage of virtual tools, which help to faster develop new materials. And we built up a platform for this, and this platform is called DigiLab. And the major goals of DigiLab are reduction of development cycles, reduction of development costs, improved material properties, and an improved material and process understanding. The first tool we are using here are analytical models, means mathematical models to predict the properties of the materials. And what you can see here are some of the models we are using for prediction of the elastic modulus, so of the stiffness of the materials. And here you can see some of the models we are using for the prediction of the strength. All those models differ in their mathematical outline. However, the more complex your material, the more complex, of course, the mathematical formula you have to use to predict the properties of your material. On this slide, you can see our results on mathematical prediction of the stiffness and strength of a binary blend of polylactide and polybutylene succinate. And you can see here in the diagram on the left side that, first of all, the stiffness of the blend goes down with increasing PBS content, and this is very well predicted by the parallel model. On the right side, you can see that also the strength is decreasing with increasing PBS content. And here you can see that not the parallel model, but other models like the porosity model or the Nicolai-Snakis model are much better to predict the slope of the experimental curve. This is due to the quite complex microstructure of this binary blend with increasing PBS content. So what are we else doing? What is very interesting as well is the usage of numerical modeling, because in here you do not predict the properties of a bulk material itself. You can predict the behavior of an actual part. So this is much more complex and much closer to the real application, and therefore we also use these kind of tools. What you also have here is a requirement profile at the beginning in which all the needed properties of the material and of the application are given. And then again, you start an optimization cycle, but this optimization cycle is not experimental, but virtual. Means you run simulation programs which give you results on the different processes, and then you do virtual optimization. And in specific, we do compounding simulations. Those compounding simulations gives us results we can use in the injection molding simulations. And again, from those injection molding simulations, we can use the results for material modeling. And if those those virtual properties of the materials meet the requirement profile, we have a virtual compound. If not, then we have to redo the compounding simulation, injection molding simulation, and material modeling. However, at the end, you end up not with a real compound, you end up with a virtual compound. And this can be used to design and to model a virtual part. And in here, we have much faster development than with the experimental trials. We have much less costs, and this brings a much faster development and reduction in time to market. In the compounding simulation, we work with the software ANSYS Polyflow. So this is a software where you can calculate the residence time, for example, as shown here, of a twin screw compounding machine. You can also simulate the shear stress over the screw. And especially in the mixing sections, this is very interesting because there you have the development of the microstructure of your compound. And this is very important to optimize properties at the end. And of course, if you find out that the screw design you are actually working with virtually is not optimum, you can do virtual design optimizations. And this helps you to find the optimum design and process properties. In the injection molding simulation, we work with the software Modix 3D. And the same here, we can differ the material properties like viscosity or flow behavior. We can also differ the processing parameters. And by doing so, we can find optimum process setup and also find out how the material behaves under the processing. And for us, this is very important because this is the final step in our optimization cycle, which can have influence on the microstructure of our materials. So variation of morphological and microstructural parameters can happen. And this is very interesting for us to find out by those simulations. And in doing so, we find information on necessary material, process, and design adjustments. So what is the general approach to optimize those processes and materials? At the first step, you have to do the design and meshing of your numerical model. In the second step, you have to define the process parameters of your virtual process. Afterwards, you must define the flow parameters during the injection molding in this case. And after the simulation is done, you have to analyze the simulation results in order to get all the information you want to have. In our case, this is the development of the microstructure. So we use a certain analysis, which is called Grace model analysis. And after the Grace model analysis, we can do the particle size prediction for those compounds or blends. And how this works, I will show you on the next slide. So in here, you can see the Grace model and the capillary number, which is the key parameter in this model. So the capillary number is the quotient between the viscosity of the matrix of your compound and the applied shear rate during processing. And this is divided by the interfacial tension of your polymers. And whenever those two quotients meet each other, you have the so-called critical capillary number. This is the red line in the lower diagram on the left side. And whenever the capillary number is bigger than this critical capillary number, you will have particle breakup, means you have a refinement of your microstructure, of your morphology. And this again is depending on the viscosity ratio of the polymers you are using. And what you can see here on the right side is what happens if we have different viscosity ratios of the matrix and the dispersed phase. So if the viscosity ratio is close to 1, you will have this relay breakup, which is a deformation of droplets to fiber-like structures, and then the breakup to smaller droplets. If the viscosity ratio is smaller than 1, we have this necking effect. And if the viscosity ratio exceeds a factor of 3.8, experimentally, you won't find any breakup anymore, and you will stay with big particles. What you can see here are the results of our rheological experiments on PLA and PBS. And you see on the left diagram that we had much different rheological behavior of the two polymers. So the PBS had a much higher viscosity and a much more shown shear thinning effect of the flow. So a strong decrease of the viscosity with increasing shear rate, whether the PLA is more or less constant in the flow behavior. We use these data to calculate the viscosity ratio of the two polymers, and this is shown on the right side. And here you can see that with increasing shear rate, the viscosity ratio comes close to 1. And if we remember one slide back, the particle breakup in this region of a viscosity ratio close to 1 is preferred in the necking mechanism. And this is very interesting for us because at injection mold or during injection molding, you have very high shear rates. And this means that during this processing, we will have variation in the microstructure. And this was also shown in the experimental results. So what you can see here is the pictures of the scanning electron microscopy of the microstructure of the blend of PLA and PBS with a composition of 80% PLA and 20% PBS. You can see on the left side the microstructure for a flow rate of 16 cubic centimeters per second, in the middle of 48 cubic centimeters per second, and on the right of 96 cubic centimeters per second. And you can clearly see that with increasing flow rate, we have a decrease in the particle diameter. And for us, this is a very important information because this will clearly change the mechanical properties of our material. So based on these results, we did the capillary number calculation for our blend of PLA and PBS, and this is what you can see here. On the left side, you can see that the capillary number for all of those blends during injection molding was above the critical capillary number. This means we had breakup during the process of our droplets. And of course, this has an influence on the properties. To predict the final diameter of the microstructure, we used the WU model and the SERPI model. And as you can see on the right side, the SERPI model was much closer in prediction of the diameter of the droplets than the WU model, and this gives us certainty in the next step, which is the material modeling, means the real prediction of the final properties of our material. This step is done with the software Digimat. In Digimat, you can define your own material, your own microstructure of your material, and then transform this into a material model, and finally predict material properties by numerical simulation. How this looks like, you can see here. So on the left side, you can see the microstructure again of our PBS PLA blends with different compositions. So at the top, you see the microstructure, the blend with a composition of 80% PLA, 20% PBS, in the middle of 50% PLA, PBS, and at the bottom of 20% PLA and 80% PBS. This information was transported by numerical modeling into virtual compounds, means we created the virtual microstructures, which is shown on the right side. And for those materials, we did numerical simulation for the tensile test, and the results you can see here. So actually, we got very good overlapping of the predicted, means numerical simulated material behavior, and the experimental material behavior during the tensile test of our blends. And you can see that especially at lower strains, this is very well overlapping. At higher strains, the numerical simulation does not 100% overlap with the experimental results. This is something we will work on to optimize our material models and to optimize the prediction of the numerical simulations. So how can these results help you in the development of new materials? We put those tools on our platform, which is web app called POLYKUM DigiLab. And you can see that it's free in the internet, reachable under this URL given here. What are the tools of this platform? We have recipe suggestions based on given properties. So there's a big database with already tested and simulated materials. The second tool is prediction of properties by analytical models. So we have implemented the analytical models here to predict the properties of blends and compounds, and this is what you can use online. And a new tool we are working on is a virtual reality environment to make the development of new materials and also to adjust the color of those materials. A fourth tool is the implementation of data import. So you can put your own data, the properties of your own compounds into the database, and others can find those results. And so this is a free database for new materials, which you can use as a distribution platform. As I mentioned, this tool is a web app you can easily access with all kind of mobile devices, and therefore have good connectivity to all of our customers and clients. So what I want to show you here is the latest results on our virtual reality environment. You can see that we created a complete immersive virtual room for development of new materials. This virtual room has two basic functions. The first basic function is that you can choose your own color by changing the LAB values of your material complete freely. What is also possible is that you choose already pre-designed colors designed by other customers, and therefore the development of new compounds with special coloring is also possible completely virtual. The second function is the three-dimensional search in our database, and you can see that we have many different material properties which can be chosen as search parameters. For example, the stiffness or the elastic modulus, the strength of your material, and by doing so you create a three-dimensional room with all the database points. You can see here, you can also choose if those points are selected, whether they are bio-based, non-bio-based, recycled or non-recycled. Based on those settings, you can define your own research room or research area. If you find your specific material which matches with your required properties, you can also check the microstructure of this. As we have seen in the previous slides, that this is very important for the properties. This is a new function we implemented in our virtual reality tool. For each material, you can directly see the microstructure. I think I could show you that converting of new biopolymers into competitive products requires efficient and resource-saving material development. We have created a virtual development platform called DigiLab for this, and in this we are working with analytical mathematical models, we are working with numerical simulations, and we are also using virtual reality tools. And by doing so, we want to help biopolymers as new materials to enter the market very fast and to improve the sustainability of their products. I have to acknowledge that this work was co-funded by our federal state of Saxony-Anhalt. Very much thank you for this, and I would like to thank you for your attention. And I hope that you have questions, and if so, then I would be very happy to answer this now.
Hello, Patrick. Nice that you are back and gave us an interesting presentation and introduction into your topic. Hello, how are you today?
Hello, a warm welcome from my side. Thank you very much for having me. I'm fine.
Okay, great. Perfect.
Hi, Patrick.
So,
Hi.
yeah, so we have already a few questions from the audience, which I would like to forward to you. The first question is, you have shown the modeling of a binary blend system. Is it possible to model compounds with more materials as well?
Yes, so what I've shown you is a quite easy or less binary system. So PBS PLA is a very interesting system. We already worked also for ternary systems, means we combined 3 different polymers. And of course, then you have to adjust the models and everything gets a bit more complex. Also, the numerical modeling and the morphology investigations get a bit more complex. But yes, it's possible to research also on multiple phase systems. But in our case, more than 3 components is not quite efficient to model, because the 3 major components of a system will have the most influence on their resulting properties. And this is the approach we have right now. We go up to 3 components, and this is what we have already online in the app.
Mm-hmm. Mm-hmm.
So there, it is quite vital, the net, and there is coming a question in. It's a little longer question. I just read it. So in first step, you have to do compounding tests to see which model, e.g. for tensile strength, can be chosen. Afterwards, you can run just simulation tests for molding, etc., and no actual experiments are needed. Is this correct?
Yes, so our primary goal is to give a good assumption or a good prediction of the properties, not a 100% right prediction. So we want to be as close as possible, of course, to get a tool which maybe reduces the amount of experiments needed to create a new material. So as we all know, many experimental trials are usually needed, maybe 20, 30 trials to get the final product. By using our tools, we want to reduce this amount of experimental trials by at least 50%, so that we maybe end up with 10 trials which need to validate the results of the simulations and of the analytical models. And this is the key to have a faster time to market.
Mm-hmm.
Okay, so sounds good.
Yeah.
We just got the information that we shall only do one last question. There are plenty of more questions.
Mm.
Okay, what would be the best composition of PLA, PBS composites to be used in packaging application?
Yeah, this is a very complex question and complex answers. Of course, this depends on the product. So, of course, it makes a difference if you have an injection molding, thermoforming, or any kind of other process. The stiffness, as you have seen, is strongly dependent on the composition of PLA, PBS, and also the thermomechanical properties. So the more PLA you add to PBS, you will also have a decrease in the thermomechanical properties. So if the heat stability or mechanical properties at higher temperatures are relevant, then you should have a quite high PBS content.
Okay, thanks a lot.
Yeah, thank you very much for answering the questions from the chat. And we're wishing you lots of luck, most of luck with your project and with blending compounds. And thank you very much for joining us. Have a good day.
Thank you very much, and have a nice conference. See you. Bye-bye.
See you. Thank you. Bye-bye.